Welcome back to the conference. I'm Steve Plote. I'm on the program committee, and I'll be moderating this session. This is a 2-hour tutorial on optical components and optical technology and implementation, and how these different components work with each other as well as against each other. So as a reference, this is part of, or if you will, key to what we've had for past optical components specialists like Richard Steinbergen, if you guys remember Richard, or Jeff Bennett from Infinera when Jeff was back at Infinera before that all changed around. So I'd like to basically welcome on the stage Chad Lamb, who comes from XKL. They're actually just up the road in Redmond, so not too far away for a trip for him. And he will basically talk about all the implementations associated with DWDM optical networking concepts and technologies. Chad's the principal solutions architect at XKL, and I'm going to let him go ahead and talk through stuff. What you're seeing on the screen is a QR code that will allow you to access some questions that he'd like that you guys can answer, or you can pose to him at the end if you can't answer the questions yourself. Fair enough? So without further ado, I'll welcome Chad up the stage. Appreciate it so much. Oh, also, this is Chad's second time talking for Nanog. Last time was in 2024. Yeah. Cool.
Great. All right. Thanks, Steve. Yeah, this QR code is actually a set of questions for you. So if you want to join the challenge here, just jump on that. It'll ask you your name, and that's it. And so after the various chapters that I'm going to go through today, I'm going to put the questions to you and see who's had their coffee after lunch and who's struggling. So if you want to join in on this, scan that code, and we'll go from there. I see 0 participants, so I don't know if anybody wants to join in the fun. We're gonna give away a free trip to the XKL booth over here, where you can get all the swag you want. There we go. I'll wait a minute for others to join in if they want to. While we're doing that, just a quick show of hands. Who knows what DWDM is? Okay. Who knows or has heard of 400 gig ZR coherent? About the same, right? Okay. So we're going to talk a lot about these concepts today. And hopefully you'll get something out of this tutorial. The format I've got set up here, we're going to go through various technologies, and I'm going to get through the entire thing. We'll have some time at the end for questions, but if the time permits at the end, I've got a bunch more information on fiber or protection, other concepts that I don't think we're going to get to today, but if we do, great. I'll flip through those slides too. But I want to get through these core components are the most important. So I want to make sure we get through that and get your questions addressed. All right, so I'm going to get started. I don't think there's any more. Okay. Right, you are. Okay. Here we go. So this is what we talk about today. We'll briefly touch on the elements of DWDM solutions, right? What are the components that make that up? And the deep dives here in the other chapters, optical transceivers, filters, amplifiers. Yeah, that's the core of what we're going to talk about today. IP over DWDM, that's a really hot topic. What is that? How does that work? And we'll talk a little bit about how that it plays with traditional transport stuff too. Then we'll talk a little bit about an OTDR and what that is in particular as it applies to integrated devices that are in this equipment, not your traditional handheld stuff that your field techs have. And then we will finish up with talking about ROADMs and FOADMs. So what is DWDM? Dense Wavelength Division Multiplexing. Here are the basic elements of a DWDM solution. There are others, and we'll touch on them, but in terms of building a DWDM solution, these are the things you must have. So you've got a transceiver, and I notice I didn't put this into a transponder, a muxponder, or whatever. This can go in your router, this can go in a variety of places. The point is, this is an optic that's going to provide you with various frequencies that you can combine onto the fiber. You need some kind of a filter to mux and demux. We're going to talk about the different filter technologies that exist today, the most common ones. The EDFA, erbium dope fiber amplifier, we're going to push into that as well. You need to amplify these signals, so it's good that you understand that how those work and what the trade-offs are for EDFAs. And then, of course, you got the fiber. So there are other elements to a DWDM system, monitoring, OTDR like talked about, optical protection, a variety of things. We'll touch on that as well, but to build a DWDM solution, this is what you need. Muxponders, transponders, routers and switches, obviously you need some place for the source of the data. These generally are going to come out of your pluggables, optical transceivers, you need your optical cables. I've left out of this talk the fiber and fiber characteristics and a lot of details about the fiber, but I do have those slides here, and you can download those off the website. So you can always look at that afterwards, you know, hollow core, etc. And then there's the optical line systems, the filters, the amplifiers, channel monitoring and equalization. What is that? I'll explain why that's important. And then, of course, lastly, the fiber. So here are your basic elements, right? Layer 2 and 3 devices, switches and routers. Layer 1, your muxponders, your transponders. And some people like to call that layer 0. I'm not sure I'm on that camp, but generally that's your physical cabling, right? That's your power and whatnot. But I listed it here as just the line system. That's things that the amplifiers, the filters, your ROADMs, etc. Just calling that layer 0 for a little distinction in this talk. And then, of course, your transceivers. Variety of transceivers. We're going to talk about these as well. You know, the good old days of 10 gig on-off keying. Yeah, that's all gone, right? So we're at 400 gig, 800 gig, and that enters another layer of complexity for you. We hear this time and time again on mating these things together and the various cables that you need. So we're going to talk about that. I like to show this. This is an older AI search, but you know, what is a muxponder and a transponder? You hear these terms all the time. This is a definition that probably migrates over and changes over generations of the product, but a muxponder is a device that's going to combine a bunch of lower data rate signals into a single higher data rate signal. So you might want to combine a gig-E, 10 gig-E, 100 gig-E, SONET, fiber channel, etc., into, say, a higher data rate OTU signal. Whereas a transponder is not doing that. Transponder is simply converting something from, say, 100 gig-E to 100 gig OTU. So it's just that one-to-one. So this is the definition we're going to use here today. So just a little graphic of what I just said. So a 10 by 10 muxponder or switch is going to take you 10 by 10 gig signals and pack it into a 100 gig signal, 100 gig frame. Or in this example, 4 by 100 into a 400, right? So technically that's a muxponder. And then a transponder, just a one-to-one. So 10 gig-E, 10 gig-E, maybe you're doing gray optics, short reach stuff, and converting that to long reach, DWDM, or same thing for the 400 gig, converting that to a 400 gig ZR. Okay, so that's our definition here of transponder. And then the filters. We're going to talk about optical filters. These are the three most commonly used in DWDM, CWDM stuff. TFF, a thin film filter. An AWG, a rate waveguide grading, and a wavelength selective switch, a WSS. We're going to talk about each one of these separately and compare them, do a little contrast. What are the advantages and disadvantages of each? On the amplifier side of things, EDFAs, erbium dope fiber amplifier. And by the way, at the end of the slide, I've got a glossary with all the acronyms and everything, so don't feel like you got to scribble anything down or take pictures, right? It's all there. EDFA, Raman, an SOA, and a ROPA. What are these things? What might you see in a common DWDM network? And what are the differences between these types of amplifiers? Okay, let's jump right in and start talking about transceivers. This talk is not going to dive into the details of how you make a coherent transceiver. It's got the optical hybrids and muxpender interferometers and all kinds of good stuff. And I just bumped it and lost everything. Oops, what happened? Thinking. Coming back? Okay. Yay. All right, I'll keep my hands out of the conversation. It's not quite there. Yay, thank you. So for the optical transceivers, we're going to talk a little bit about the specs and the standards, and I will try really hard to not put you to sleep. We're not going to get into the hundreds of pages in the specs, but I want to show you where they are and what to look for. Some of the transceiver naming convention, that's got some interesting components to that. And then, of course, connector types, which can be super frustrating, especially if you have techs that already have various things in their bag of goodies, and oops, it doesn't quite work with the new 400 or 800 gig transceivers. And then we're going to talk about modulation schemes. There's a couple elements of modulation schemes that are really important to understand when it comes to amplifying signals, looking at OSNR, spectral efficiency. So from that point of view, we're going to talk about modulation schemes. So back in 1990, the SFF was formed, Small Form Factor Committee, and they created some specifications. What's the electrical spec? What's the mechanical, the management? And so this was the beginning of creating some MSAs and standards for transceiver vendors to design to and for equipment vendors to design to, right? So they can talk to these devices. So this is an example of an SFP, but this is the first of these specs. And then more recently, with 100 gig, 400 gig, and higher data rates, the CMIS spec started by the OIF, and this was really necessary, right, to make these things industry standard. You can buy them from multiple vendors. System vendors like XKL can rely on the registers to be in the right place when you go to read the data and report statistics, right? So these specifications are really important. And this is also what has really enabled the 400 gig coherent ZR, ZR+, and the interoperability between vendors. This is just the management side, but this was really important for this stuff to be able to go into a device and for you to be able to get accurate reporting about the statistics and counters in that device. And then following the CMIS was the CCMIS, the coherent side of the CMIS. And so just a couple links here that you can look at and a little bedtime reading for you. So the IEEE, one of the entities that's heavily engaged in helping create these standards, refers to a lot of the transceivers in this form here, 10G base LR, for example. So that refers to the data rate, 10G, 10 gigabits, the distance, the reach, LR, long reach, right? So this is how this came about. And as things grow and data rates get higher and you start using different modulation schemes, different number of lanes, the scheme expands from there. So 100G base LR4, very common 100 gig interface, is going to be using 4 lanes, LR4, that's what the number 4 refers to. So you can see here, if it doesn't have a number, typically that means 1. But a more common convention is sort of this coupling of the IEEE spec and some of the MSA stuff. So when you're looking for a transceiver for whatever your application is, you're generally going to see something like this, 400 gig QSFP DD LR4. So there's your data rate, the form factor, QSFP DD, there's OSFP, right? There's a whole bunch of different form factors, so it's really important that you understand what the device's package looks like. Then you have the transceiver reach. I'm going to talk about that a little bit. So, but that's also equally important for a couple reasons. Not just does your transmission, is it going to work? Do you have a long enough reach device? But there are other components to that, like different frequencies getting used and problems with doing that kind of interfacing. And then lastly, the number of lanes at LR4. So that refers to the number of optical lanes or wavelengths. So yeah, I know this is not really great. It gets worse, right? So 800 gig, more lanes, more stuff. So you need something to rely on to understand what you've got. This graphic is just to show you sort of physical stuff, right? What's the basic size of these things? OSFP is a little bit bigger than the QSFP DD, so you get a little bit better heat dissipation out of that. But you know, the size is significantly different. And this doesn't necessarily count like what's inside the device that's hosting it. You've got a bunch sticking out, right? So that door on your cabinet doesn't quite close anymore with all the advantages of the new technology of putting erbium doped fiber amplifiers inside the transceiver. So they've stolen some of the space out front. But this is the envelope that they have to fit it in. And then here are the most common devices. There are more than this, but when you see these terms, you'll have a good understanding of what's what. So a direct attached cable, a DAC, AOC, AEC. So these are going to be those short cables that, you know, if you're just going within the rack, right, you can just connect and save some money on optics and whatnot. Short reach, very short reach is short reach. Short reach, that's a multi-mode, right? So that's going to be, you know, next rack over kind of thing. And now you start getting into the more complicated. The DR is a data center reach. I can't tell you how long it took me to figure out what the D stood for in DR, but data center, 500 meters. So anybody that works with these components, that's your magic numbers. You start going, oh, 500 meters, 2 kilometers, 10 kilometers, right? These are all the magic numbers. And here's what they mean. So the DR got extended with the extended DR, and thanks to, you know, some entities called it an XDR and others called it a DR+. But that's a 2 kilometer device, much like the FR 2 kilometer device. So, you know, do they work together? I mean, are they compatible? And the answer is, it depends. So we're going to talk a little bit about that too. What makes that work? The LR is by far the most common and the most expensive of these shorter reach guys. And then PLR, parallel LR, talk about that. And then we get up to the ZR, that's your standard for like 80 kilometers. Back in the 10 gig days, that's what the DWDM devices would reach. And today, the ZR, same thing. But it's actually 120 kilometers, but close enough. And it's really important we talk about connectors. I know, super boring, right? Why do we care? Let's just get the cable, plug it in. Well, with the advent of the 400 gig stuff and multiple fibers and MPO connectors and all these other things, it's become very complicated. We're going to talk about that here in just a second. But basically, the connector, that's the place where you can connect these things together. So traditional cable, the optical cable at the bottom there, that's LC duplex. Everybody understands that one, most common. That's the most common thing that your tech's going to have in the bag. But things have migrated to more complicated things. Now we have a CS, which is a compact small form factor. We have the dual LC, when they turn the LC sideways. You got a mini LC. And this is just to name a few. So you can see if your tech is sitting there holding this cable and he's looking at a transceiver with a dual CS, those LCs just aren't going to plug in there. So you need to understand what you're buying before you send your tech out to go plug something in. MPO, multi-push-on connectors are very common, 400 gig and 800 gig, right? So this graphic is a little misleading because those MPOs at the bottom of the screen there, you can clearly see the 8 fibers, they're lit up, 4 on one side, 4 on the other. If you actually had that cable in front of you, you wouldn't see that. They're all dark. You could barely see that there's one row of connectors. The 12 fiber looks exactly like the 8 fiber. They just didn't put 4 fibers in the middle. And notice the keying is identical. So nothing to prevent you from plugging in a 24 fiber MPO into an 8 fiber socket. Sorry, I didn't do it. It's not my fault. But this is what you have to deal with. You got to know what you're doing, and you got to know what the cables are. You got to look at cable part numbers. You got to look at the transceiver itself. So on the top left there, that's an MPO8. That's the most common 4x100 gig. So if you got a 400 gig transceiver and it's a 4x100, a PLR4, a DR4 plus, that kind of thing, that's what it's going to look like. And so you have to make sure you get that 8 fiber MPO connector. An MTP is just the proprietary version of an MPO. A little bit tighter tolerances, a little better on the insertion loss, but they're interchangeable. Okay, getting into 800 gig, you're going to find a dual MPO8. So they take 2 of those MPOs, turn it sideways, and there you go. That's a very common for 8x100. Yeah, and then I thought it was interesting to show the MPO12 2-row, since it looks exactly like the 24. And so how do you know? Here's a very common example of a 400 gig optic, right? MPO8 on one side, and you want to break that out into 400 gig streams, 400 gig interfaces. So in the top left guy, I show a 400 gig DR4, XDR4, or PL4. These are the different options for getting 4 lanes of optics out of that transceiver. And it's going to mate with the corresponding DR, FR, LR. So that's how that mating would work, right? Match up the letters. But a DR can plug into an FR. A DR can plug into an LR. There are some limitations on how that works, but optically speaking, it works just fine. And any of these kind of details, you want to ask me questions afterwards. Happy to explain in more detail, but I only got 2 hours here, and you'd be surprised how long this is going to take me to get through. So in the bottom one, a little more detailed example with a DR4 400 gig transceiver with this MPO to LC breakout cable going to 4 separate 100 gig DRs. Okay. All right, so what's wrong here? I've got a 400 gig PLR4 with the MPO breakout cable going to 400 gig LR4s. Should it be, I'm sorry? Okay, you can't answer any more questions. Too easy for you. Yes, precisely. So each one of the wavelengths in a PLR4 is running at 100 gig. So optically speaking, the 100 gig transceivers on the other end, each one of those has to be running a single wavelength 100 gig. So an LR4, that's 4 wavelengths of 25 gig. Doesn't work. This is extremely common because the 100 gig LR4 is really popular, right? I promised I wasn't going to get into the architecture of these transceivers. So this is just it. There's the only slide I've got on this stuff, but just to contrast the technology improvement. So on the left-hand side, we've got the SFP technology. Simple TOSA, simple ROSA, very basic management. TOSA is a transmit optical subassembly, and the ROSA is the receiver optical subassembly. So these are how these things were built. Now let's jump way ahead to 400 gig and 400 gig coherent specifically, but this also applies to some of the longer reach non-coherent stuff. And the TOSA is now a much more complicated optical assembly, photonic integrated circuit. It's got a muxponder interferometer. It's got, you know, a more powerful laser. It has an amplifier. It's got a lot more stuff. Similarly on the receiver, optical hybrid receiver is needed for coherent reception. You got your modulator, your demodulator. You got all these different modulation schemes. A lot of stuff going on there. And oh yeah, the DSP, the big power hungry device that's in there, right, to do all the recovery and submit transmission of the signal. So it's a great advancement, but the complexity is enormous. And with that comes a lot of statistics, counters, and everything else that's wonderful for your network. And so, you know, it's not free, but it's, you know, how else are you going to make this work? Here's an example of a variety of the most common modulation schemes. So I mentioned a minute ago the single wavelength 100 gig. So that's an SR-DRL, FR-LR, so there's no number afterward. That means it's one wavelength. Here are the different optical and electrical modulation schemes that are being used for these devices. And you can see PAM4 is very much the most common, and we're going to talk about what that is. But this is really good reference, right? So if you've got like a DR4, 400 gig DR4, like that example I showed you, you've got to hook that up to 4 regular DRs, but it also hooks up to the FR. It also hooks up to the LR. So, you know, you talk to your vendor or Google it. Hopefully you'll get the right answer. No guarantees there. But it's important to note that there are a lot of variations in modulation schemes depending on the type of device you're getting and how far the reach is, and then the cost and power consumption is equally in line with that. And then at the bottom, I'm showing the 800 gig. Not many people are there yet, but that's what some of the more common standards are for 800 gig. So LPO, CPO, DCO, what are these things? In case you were wondering, so in a lot of AI clusters and areas where you've just got to cut the power back, these are very good technologies to help do that. So at the top guy, the DSP pluggable, that's what I just showed you, 400 gig ZR DCO. That's got all the stuff inside. It's got the DSP, all the optical transmit, receive, everything that you need is in the pluggable. And so that's connected to your board, the router or the transport gear through this cage, right, a QSFP DD cage, and that connects to some ASIC that's on the board, a switch. Hey, I didn't touch anything. There we go. Oh, what's happening? I'm not touching it. I'm not going to touch it. Well, so I can keep talking. So the LPO and CPO, you've probably heard about these things, right? So these are the co-package optics and the linear pluggable optics. You know, like, this is great stuff. Why wouldn't I buy those transceivers? They're lower power. They're, you know, better for, you know, meeting my power budget, meeting my cost budget. Well, the problem with that is, you know, these LPO, CPO guys, they require stuff on the board. So that ASIC that's on your board, that Marvell or Broadcom or whatever the chipset might be, it has to do that heavy lifting that was done by the DSP in the pluggable. So we're just moving that complexity back into the chip, right? So that's great. That works wonderful, right? The LPO here, the DSP is really dumbed down. And so maybe you've got a, oh, you gave me yours. Yeah, there we go. Okay. So the LPO, that'll work great as long as that ASIC, the Marvell chip or whatever you're using, can handle recovery of those signals, right? So we can take some of that complexity out of the pluggable and put it onto the board. And the CPO, even more. So now we're actually putting the optics on the substrate with the ASIC. So now you just have a front panel plug. There's nothing there. There is no pluggable. So, but this only works, right, with the highest of high-end switch chip or router chip. And so your options are not just, oh, well, let's just go with a CPO. That'll be better. No, you've got to have all the infrastructure in place already. But I wanted to touch on this since there's a lot of buzz, especially with the power consumption in these AI clusters that we keep hearing about, and they keep moving stuff away to other data centers because they just don't have the power. This isn't going to just be a panacea and solve all your problems. You're going to have to move the technology to accommodate the LPOs and CPOs. Okay, we're going to get into a little bit more about modulation schemes, and to do that I need to talk about baud rates, and to do that I need to talk about what it means. So this is a simple example of a signal we're trying to transmit 1 bit per second. So every clock cycle here we're transmitting a bit, and it's a logic 1 or logic 0. So we're trying to transmit this pattern 110 100. So you can see by the H dotted line, we're capturing the value of that signal. So you can see the pattern, 110100. So this is a bit rate of 1 bit per second and a baud rate of 1 symbol per second. We'll call it a symbol, introducing this term. A symbol is going to represent multiple bits potentially. In this case, the symbol is only 1 bit. So the bit rate and the baud rate in this example is 1 bit per second and 1 symbol per second. Now I introduce a more complicated modulation scheme like PAM4. I have 4 levels of logic, and I'm encoding 2 bits per symbol. Okay, so each sample is now, I'm getting 2 bits, right? So it takes me half the time. So I've got a bit rate of 2 bits per second. Okay, but my symbol rate is still 1 symbol per second. So that's my baud rate. So this is a distinction that's really important. I like showing this example because it's something you can look at and get it, right? It makes sense. Now when we get into the more complicated modulation schemes, QPSK and QAM, now you can start to understand, you know, what the heck's going on with this you know, the baud rate, and why is this guy better or worse, or higher baud rate and lower baud rate, and what does that mean? And we're going to talk about that here in just a second. So here's just a collection of a variety of devices, and we're going to talk through this, and I'm going to show you how you can calculate this. But so for a 100 gigabit signal, the actual data rate for that signal is about 120 gigabits per second because you've got overhead, you've got forward error correction. So we just call it a 20% overhead for that. So I'm trying to transmit 100 gigabits per second, but I actually need 120 gigabits to do that. Okay, so my modulation scheme is DP-QPSK, very common for the 100 gig coherent. So the baud rate for that is going to be 30 gigabaud. Basically, you're going to take that 120 and divide it by the number of bits per symbol. I'm going to show you the equation in a second. And so there's QPSK is 4 symbols, 2 bits. So 120 divided by 2 is 60. But now it's dual polarization. That's what the DP stands for. So that means I've got 2 polarizations of the light that I'm putting data down. So I'm putting 30 gigabaud down one polarization and 30 gigabaud down the other for a total of 60. And then the channel requirement for that. And I'm going to get into this some more later. I'm going to show this same table, but I want to introduce this to you now so I can talk about something else. So if I went down this list and I'm looking at all these different devices and data rates, it's all well and good, but why do I care? And I want to just zoom in on this one for a second. So in last generation of 400 gig, QAM 16 is the most popular modulation scheme. And it's got a 60 gigabaud baud rate, okay? 75 gig channels. And again, I'm going to tie all these things in later when we talk about the filters, spectral efficiency, et cetera. In today's generation of 400 gig, I can now do that with a QPSK modulation scheme. So that's an advancement for noise and reach, but it's a disadvantage when it comes to the bandwidth that is required to transmit that signal because the baud rate is double. So in a QAM 16, that's 4 bits per symbol. In a QPSK, it's 2 bits per symbol. So that's really simple math. So you can get more or less efficiency out of your fiber utilization, but the important characteristic here is about the reach. A QPSK signal is going to go much, much further than a QAM 16. We're going to talk about why that is. So this is about the extent of the math we're going to do in the tutorial, but it's pretty easy math. Basically, the baud rate, you could think of the channel requirements as being about the baud rate, but then there's these things called filters that are involved that you have to use to get your data onto the fiber. The filters are not perfect. They're not perfectly square wave devices that are going to allow that signal to go through. They have edges. They have this thing called a roll-off factor. So effectively, you need a little bit more bandwidth to propagate that signal through the filter and onto the fiber. So that's why I do the baud rate example here, 60 gigabaud in this calculation for this particular modulation scheme. That's why it requires a 75 gig channel, not a 60 gig channel, because you've got to accommodate the filter. And we're going to talk some more about that. Okay. Let's go to our questions, see who's been paying attention. What does the acronym, and your phone might go to sleep while we're doing this stuff, it'll wake up and the website will still be there. What does the acronym DWDM stand for? Okay, I'm easing you in here to a nice, easy question. I think we had about 30 people participating, so I'll tell you. I'm not going to spoil it. I have to wait. So once that number gets up a little higher, then we'll move on. Come on, this is the easiest one, so get your points now. All right, about done. 24. Anybody else? Okay. Yes, it was 2. How many optical wavelengths does a 100 gig FR transceiver use? How many wavelengths? 1, 2, 3, or 4? I think I was supposed to hit that solve now button, sorry. 1, 2, 3, or 4? All right, 25 seems to be the magic number. Yeah, just 1. Good. How many optical wavelengths does a 400 gig LR4 transceiver use? How many wavelengths? Yeah, you guys got this. Too easy. It's 4. All right, so what's the baud rate for this? 100 gig PAM4. 100 gig PAM4. That's 2 bits per symbol. What's the baud rate? Told you it was going to get harder. One more. You out there? There you go. Right, so take 100 divided by 2. Okay, that's your baud rate. All right, good. Okay, so I've got a 60 gigabaud signal, requires 75 gig of spectrum. So it's 60 gig plus a little bit more for your imperfect filters. How much spectrum is required for a 120 gig signal? How much spectrum? How wide your filter have to be? Oh, 26, okay. Right. So it's basically the baud rate plus your fudge factor of the filter. Okay. All right, filters. Let's get into it. So the most common filter types, thin film, AWG, and the WSS. The thin film and the AWG, those are passive filters. No power required. The WSS, that's an active device. So for all of these filter types, this is an important principle, is this principle of interference. This is how these filters work. Show of hands, how many people have been tubing behind a boat? All right, that's enough. Cool. All right, so I love to torture my children and always wanted to give them the maximum thrill, right? So you're trying to create this wake behind the boat, and you kind of do a little bit of a circle, like a slow circle, and those waves are, you're forming these big waves, right? And when these waves collide with each other, they're interfering with each other. And they interfere in two ways, constructively or destructively. So I want to get those those waves coming in at each other, and I want them to amplify. I want them to be double what I could produce by the boat. So that's the left side here, this constructive interference. I've got two waves propagating toward each other, and when they are interfering with each other, they're adding, they're additive. And then similarly for the destructive one, which my kids hated because nothing happened, I'm sorry, I missed it. They counteract each other. So that's in the water. It's the same thing in sound. Well, guess what? It's the same thing for optical signals. So this principle is what's used to build these filters. So I'm going to send here, we're going to go through an example here with a demux filter. So I've got my DWDM signal coming in. I've got 4 colors, and I want that filter to separate those 4 colors out so I can send to the 4 receivers. So in the thin film technology, I think everybody understands that, you know, sunglasses help to filter out the light, right? There's a film on the glass. A thin film filter is many layers of material on a glass substrate, carefully engineered to pass certain frequencies and reflect others. And in doing so, you can build a channel plan. So in this example here, I've got 3 different colors, 3 different filters, F1, F2, F3. So I'm going to send all my DWDM light into the first filter, and it's going to pass the red and reflect all the others to go on to the next filter. And similarly, it's going to pass the blue and so on. So this is a very common thin film filter approach. And probably the most common filters for smaller channel counts, anywhere from 4 to 12, 16 channels. When you start getting to more channels, this cascading effect starts to be a little bit more problematic because you got a little bit of loss each time you're hitting these filters, and so it doesn't really scale well unless it's done well. Which, come by the Xscale table afterwards, I can show you how it's done well. But this is a very common technology, and it's been around for a long time. So this is referred to as thin film because they're laying the film on top of the substrate. An AWG filter. This is where you, similar principle of interference, except the channel counts are much higher. And what we're going to do here is we're going to feed the input light and spread it out to all of these little guides. See the 4 black lines. So this is a 4-channel AWG, which doesn't really exist. It's much more channels. But for example here, I wanted to show you that if you looked at all 4 of those guides, you'll notice they're not the same length. So that has an effect on the phase of the signals passing through there. It takes longer for the light to get through the longer one than the shorter ones, right? And so by using that principle of interference, coupled with this, these guides or these gratings, you're able to direct certain colors out the fiber on the other side. This is an X-ray of the chip. So there's your waveguide, and you can see the bunch of channels and different length paths that the light has to take. So this is a really good example of how this works. So it's a chip. It's manufactured. It's not a bunch of fibers, not layers of film like the thin film. And this is why it's so commonly used for many, many channels. It's got a lot higher insertion loss, but it can accommodate 96 channels. And then the third type would be the WSS. This is the most common technology today, which is called an LCOS, liquid crystal on silicon. Liquid crystal, LCD. I think everybody in this room probably knows what that is. This is a similar technology. So the way this works is, again, I'm just showing you a demux, but everything's the same in the other direction for a mux. My common port there in the middle, all my colors are coming in on that common port, and they hit a grating and some optics. I'm really simplifying this, but the idea here is that grating is going to separate the colors and shine them individually on an area of that, that LCOS chip. So the red's always going to shine there, blue, green, etc. And by applying a voltage to the LCOS chip, you're able to adjust the phase and direct where that light is going to go. And you can see in this example here, the dotted line is the result of doing that. So I can adjust the red and have it go out to, say, that port, switching port 4. So this is dynamic, right? So this requires power, but this is the basic capabilities or the basic architecture of your ROADMs using an LCOS WSS. And we're going to talk a little bit more about this in the last chapter. Another key principle then with all of these filters is how well the filter separates the channels. So if I've got red, green, and blue going through my channels, I don't want any red on my blue. I don't want any blue on my red. So adjacent channel isolation is an important spec when you're looking at what kind of filter technology to use or what you really need for your network, so more importantly. So it's the ability of a filter to prevent light power from other frequencies to pass through this current band. So that's the idea behind adjacent channel isolation. So if I've got red spilled over in my blue channel and blue's trying to, the blue receiver's trying to receive that light and it sees some of the red, that's noise. It can't recover the blue if it's got too much red noise in there. So that's what the result of ACI is. So quick comparison then for these 3 technologies, thin film AWG, kind of lump them together because they're passive and they have more similar properties than the WSS. So insertion loss wise, the WSS is a much higher insertion loss. The thin film is by far the lowest insertion loss, and the AWG is right about in the middle. What is the result of that? More amps. And then we'll talk about what that means. Why is that a problem? PDL, polarization dependent loss. So I mentioned for the coherent signals, the modulation scheme is DP, dual polarization, DP QPSK, DP 16 QAM, etc. That means it's using both polarizations of the light. Well, PDL is a phenomena where the insertion loss on one polarization is different than the other. And so that causes problems for these signals. So you can't have part of your signal arriving earlier, later, power level wise, being able to recover it. So PDL is an important property in these filters. You can see here that thin film and AWG have a much lower PDL value. Higher PDL means poorer performance. And then lastly, is it just me? Am I just the lucky one here? Am I standing in the wrong place? There it is. Sorry to keep you guys working over there. I swear I didn't touch it. And then ACI here. So this is how much suppressed the adjacent channels are. So 28 to 40 dB. The bigger that number, the better. I don't want red on my blue channel. So again, you can see here that the WSS is poorer performing than the thin film and the AWG. So you've probably heard lots of things about ROADMs and their virtues, and the passive filters are just not as flexible, and they can't do all the things you want to do, but there's no free lunch. So this is showing you some of the costs associated with the different technology. And we're going to talk about what does that translate into for your network. We'll talk about that in next chapter. So the electromagnetic spectrum, I want to jump into this real quickly to just show you what optical communications typically uses. I had to throw this one up there just to show you the beautiful picture. We're not going to talk about that guy. Let's use the dumbed down one. So this is just showing you the different frequencies. So you've got AM, FM, you've got Wi-Fi, you've got cellular, right? You have all these different frequency spectrums that are allocated by typically the government to allow different technologies to use the spectrum. And it's no different in the optical domain, in optical communication. So for DWDM stuff, we're at about 192 terahertz. 192, 193, 194. That's where the optical communication stuff sits, typical DWDM signals. And this is how it's carved up. So you have these different bands. No particular naming convention here, nothing fancy, original, extended, short, conventional, long, ultra long. But this is where all of the communication stuff is where the lasers are tuned to these frequencies. The filters are built based on these frequencies. So it's important for all the vendors to rely on this. And the C-band, that's your most popular. So when you're looking at DWDM equipment, you're going to start with C-band. And then if you're a big user of equipment and bandwidth, you might need L-band also. So that's when you see C plus L, that's what that's referring to. Why is C-band the popular one? So this chart is showing you the attenuation of the fiber, the attenuation of the glass, and as it pertains to the different frequencies of the light. So you can see that the lowest place for insertion loss is in the C-band. That's why the C-band is used, right? Because if the attenuation is too high, you can't get your signal from A to B, and you got to amplify it and amplify it and amplify it. And that's why L-band is your next most popular region of spectrum. So zooming in then on the C-band, the ITU, International Telecommunications Union, specifies what these channels are. So when you talk about channels, channel 60, channel 59, they're specific wavelengths, specific frequencies. And that's how we all can build and design these networks based on these common frequencies. So we talked about the thin film filters, we talked about the AWG filters, and we talked about the WSS filters. The top two diagrams are trying to depict what the thin film and the AWG filters, those are fixed grid systems. And so, for example, like the red arrows, that refers to 100 gig, a 30 gigabaud signal, and it requires so much spectrum. So the 75 gig grid that I'm showing there will allow you to put channels in between and the centers of those grid. Similarly, the 150, they're fixed forever. They don't move, you can't adjust them. The flex grid is what you get with the ROADM, with the WSS. You're able to adjust the size of the channels, thereby making a more efficient use of the fiber. You can put more channels on because I can use the exact amount of bandwidth I need for the different signals. So for example, the red signals running at 30 gigabaud require 37.5 gigahertz of spectrum. So I just need that much. So the flex grid, I can allocate that within the WSS. I can't do that with the other guys. So again, trade-offs. So we'll talk about spectral efficiency in a minute, but if that's a really important characteristic, if you're trying to eke out as much bandwidth out of the fiber as possible, you want to pay attention to spectral efficiency. It's a measure of how efficiently the communication system uses the spectrum. So it's basically this, at the end here, it's the amount of bandwidth divided the amount of spectrum you're using for that bandwidth. It's a simple measurement. So I like to use this example of office space. So you've got this office space you've rented for your work, and you throw some offices in there. So that's all well and good, but what's with all the white space in the middle, right? Well, that's not very efficient use. You're paying X dollars per square foot. Let's maximize what we're getting out of this. All right, so I'll put some more office cubes in the middle. Well, that's pretty good. Now I'm really efficient, right? So people per square feet, I've just bumped it up. But there's still some bigger offices, right? So let's just carve it up. This is the most spectrally efficient, most energy efficient office space wise and people wise that I can do here. So we're talking about the same thing in optical communication. So back to this example, you can see that by tuning the size of the space, to match the baud rate, I can really optimize how many channels and how much data I put down that fiber. So jumping back to that table that I showed you earlier, and the different baud rates and the required channel bandwidth, this gives you guidance when you're looking at solutions about, do I want a thin film filter, AWG filter? Do I need a WSS filter? Can I get away with the passive stuff, or do I need the spectral efficiency and that sort of thing? So this gives you that guidance, right? So if you're looking at 400 gig transmission in a DWDM system, 75 gigahertz is your channel bandwidth requirement for that signal, running at QAM 16. And if I just zoomed in at the most common, these are the most common guys that are used today. So 100 gig coherent, 400 gig coherent, old technology, QAM 16, 400 gig coherent, new technology, QPSK, and then a couple of 800 gig guys. So the baud rate is, we showed that calculation, right? Divide the data rate by the number of bits per symbol and add a little fudge for your filter. There's your channel bandwidth requirements. So when I look at that example I showed you before, where I've got old technology 400 gig and new technology 400 gig using the two different modulation schemes, my efficiency is cut in half if I use 400 gig QPSK. I'm half as efficient because the channel bandwidth requirement is double that of a QAM 16, right? So spectral efficiency is important to you. Well, maybe you shouldn't be using 400 gig deep QPSK. Why would you use that? For reach, distance. You can go a lot further. We're going to talk about why in a minute. Okay, before we jump into amplifiers, let's go to our quiz. What is the principle used in most optical filters that is constructive or destructive? Got interference, additive, adaptive, thin film. So got to wake up your phone and drop in your choice. I know it's hard to read it on your phone, but I was wondering why that timer was running out. Okay, where are the rest of you? Come on, wake up. Huh? I know. Well, I only got 10 people answering. Oh, okay. So, yeah, it's interference. What band is the most commonly used? Come on. I'm going to mix in some of these easy guys with the hard ones. So, all right. Yeah, the C band. Which one of these implementations is the most spectrally efficient? The most spectrally efficient. And the answer, oh, 19. I'll give you a minute. Ready? 400 gig and a 75 gig channel. Okay. All right, amplifiers. So the most common technologies, EDFA, erbium doped fiber amplifier. Raman uses the principle of Raman scattering. Talk about that. An SOA, a semiconductor optical amplifier, and a ROPA, a remotely optically pumped. So these are also in order of the most common. So this is what an EDFA looks like. I've got my DWDM signal coming in on the left. I've got a filter that's going to combine what's called a 980 pump laser. So that's the laser that's inside the EDFA. So I have all my DWDM signals coming in, and I have this 980 pump laser coming in. Combine those two, and that goes through a little piece, 10 meters of erbium doped fiber. So it's your glass, but it's been doped. And that's where the magic happens. So the energy from that 980 pump is going to transfer into your DWDM signals, right there. And then coming out the output there, then is your amplified C-band signals. I listed C-band here because most EDFAs, well, all erbium-doped EDFAs operate in the C-band only. So they're very frequency specific. You get outside that, you try to go in L-band, you need to dope the fiber a little differently. So that's another reason why EDFAs are, and why the C-band is so common. EDFAs work only in the C-band. So it's a really simple design. There's monitors and you know, what's the input power, what's the output power, what's the gain. There's performance implications here. So that 980 pump laser, there's no free lunch. You don't just get amplification. You also get noise. You get optical noise. And so how you operate the EDFA will dictate how much noise you put into your system. And if you have a good EDFA, it'll be a lower noise device. We're going to talk about noise figure. If you have a poor EDFA, it's just not going to work very well for your network. So this is a really important component in any network. So not only how good the EDFA was designed and how little noise it injects, but how you operate it. If you operate it at a very low power level or a very high power level, it's going to inject more noise into your network. And now in contrast to that EDFA this is the second most popular amplifier, a Raman amplifier. Very different principle here. The C-band signal's coming in on the right-hand side, so reorientate yourself here. But the action that's happening is out in the fiber, outside plant. So the concept of Raman scattering, it's a nonlinear effect in the fiber, in the glass. You're taking advantage of that with this approach. So what a Raman does is you have these different frequencies, 1450 and 1460 in this case. This is called a 2-pump Raman. There's 3-pump Ramans, there's 4-pump Ramans. The number of pumps you have and the frequencies of those pumps will dictate how much spectrum you can amplify. So this is not just a C-band amplifier. This will cover the L-band, this will cover S-band, this will cover other spectrum. But in this example here, we're looking at just a 2-pump device, which is typically a C-band, extended C-band. And here's how it works. So you've got these 2 pumps, they get combined in this combiner, except now this is a counter-propagating Raman, which means it's firing back to the DWDM signals. The DWDM signals are coming into it. The Raman is pumping in the opposite direction. Because what it's doing is it's basically reaching out and amplifying the C-band signals 20, 30, 40, 60 kilometers away. There's amplification happening all along the glass. And so it's amplifying it out there, and as the DWDM signals come in, you get more and more amplification until you get to this combiner, and then the C-band signals just pass through the combiner. And now you get your amplified stuff on the backside here. So that's how the Raman works. Operationally, the Raman is more difficult because now you're relying on the outside plant, connectors, patch panels, adapters, etc. All of that stuff has an impact on the Raman gain. There's also, which we probably won't get to, but we'll see if we start talking about fiber and laser safety and eye safety, the power levels associated with a Raman are much, much higher. And so you want to have safe operation for your techs that are out there, and you don't want anybody getting hurt. You can literally burn your skin. And this is not visible light, so you can blind yourself. A lot of bad things can happen. So Ramans are typically operated in this counter-propagating mode because you can put in safety features. Now I can, for example, inside the Raman amplifier, I can see a very low power C-band signal, and I'll know the fiber is connected. It's all there. I can see a little bit of C-band. Oh, okay, I think I'm okay. That's a safety feature. If the fiber were disconnected, you wouldn't see any of that C-band, and the Raman would have to automatically shut itself down. So that's why counter-propagating is a much more common Raman than a co-propagating Raman. You don't have that C-band signal to help you do a eye-safe shutdown. I'm not going to talk too much more about that, but you can certainly ask me more questions about it. These are the less common type of amplifiers. It's a semiconductor optical amplifier where we can apply an electric current and we can transfer some of the energy to the optical signals this way. It's just not a very robust amplifier for single channel kind of stuff, and you typically aren't going to see these used out in the solution you're looking at. And then the ROPA, similar to an EDFA, you've got some dope fiber, but it's in the outside plant. So if you happen to have, I don't know, 120, 150 kilometers of glass under body of water, and you don't want to put a subsea amplifier in, you can do something like this. Again, it's very exotic, not very common. And so I'm not going to spend a lot of time talking about it. So comparing these 4 devices, EDFA, it's used everywhere. It's the most common amplifier. It's the most cost-effective amplifier. The amount of noise, that's the key parameter, right? Noise in your system, bad. Noise is bad, right? So it's a medium contributor. And again, It's how good of an amplifier is it, and what operating conditions are you running it at. So you can have it perform more poorly if you operate it at not its optimum. But operational complexity-wise is super low, cost is low. We talked about the Raman. That's really for those longer segments. So EDFA will work for you for, say up at 120 kilometers. You can have EDFAs on the end, no problem. So if you had a much longer link, just every 100 kilometers or so, you're going to want another amplifier. But sometimes the noise contribution starts getting too great, so you need to start using Ramans. Ramans are very low noise devices. But the operational complexity and the cost are much, much higher than EDFA. But sometimes you just don't have a choice. Your link's not going to work without a Raman, for example. And your vendor, whoever you're working with, will give you guidance on it's not like, hey, I think I need a Raman here. That they should give you all the guidance you need. And then the SOA and the ROPA, these are not very commonly used devices. Let's just go through a quick example. In here, I've got two sites, and every 100 kilometers or so, I've got, I don't know, you've probably seen it, concrete structures on the side of the road with no windows, with fences around, right? That's an amplifier site. So every 100 kilometers, I've got an amplifier. And I launch my signal at site 1. I'm just going to go in one direction here. I launch my signal at site 1, and it gets to that first amp stage. So now the power level is low, and I need to boost it up. So the little squiggly line below there shows sort of the signal power now, but then I've got this other component called noise. I just added that noise at that amp site. You have a little bit of noise at the transmitter from your pluggable, but a lot more noise is contributed to the signal by the EDFAs. So I got a little bit of noise. So I have this ratio of signal power to noise power. That's the key parameter. So when you look at your 400 gig pluggables, they're going to have an OSNR spec, and they're going to report the OSNR. That's the optical signal to noise ratio. That's this ratio right here. So as I go through the next stage, I've amplified my signal at the first stage, and now I'm going through another 100 clicks. I need to boost that signal some more. Well, not only am I amplifying the signal, I'm amplifying the noise from the previous stage, and I'm adding noise from this stage. So now my OSNR was this number, now it's this number. Next stage, this number. If it gets below spec for the receiver at site 2, it's not going to work. And so you can do what I think is a fairly simple computation here to determine, is your link going to work? How many amplifiers did I have to put in? This is where you say, well, I might need a Raman because I'm not going to meet the OSNR spec. But the key parameter here is the input power. So I put all the fun equations, and these are the constants that go in it. And if you wanted to compute this yourself, you can. But the key number is your input power. The input power to that amplifier stage dictates the OSNR to the next stage. So if you can keep the signal power at a reasonably high value, you're going to have a way better OSNR, because this is cascaded as you go on down the line. So you can't improve the OSNR. Once it starts going downhill, it's going downhill. You got to turn the signal back to an electrical signal in order to start over again, right? Nobody wants to do that. That's very expensive. And so this is important. So when people come to us all the time, I've got this link. I want to go from here to there, and I don't want an amp stage in the middle. It's just that's space and power, and that's something I got to manage. I'm like, well, okay, you can skip that, but my input power when I get to the other end is going to be so low, my OSNR might not work. But still, they want to skip it. Okay, let's throw a Raman in there. We do that all the time. We just did a 250 kilometer link with a customer. That's a long ways, 250 kilometers. We got to have Ramans. We got to have EDFAs. We might have to dial the data rate down. So this is where that 400 gig signal I was talking about. Yesterday's technology running a modulation scheme of QAM16, that OSNR requirement is much, much higher than running at QPSK. So we had to tell that customer, hey, you can't run it at QAM16. You're going to need to use the new stuff running at QPSK because that OSNR requirement is much lower. So these are all these trade-offs. But the key here is to know that the input power dominates this calculation of OSNR. Okay, get your phones out. All right, yeah, I know. Too easy. Which amplifier is the most commonly deployed today? I'm looking at that timer going down. Almost there. Okay, looks good. Anybody else? Ah. All right, of course, EDFA, right? Easy. Which amplifier contributes the least amount of noise? Another easy one. Okay. The Raman. All right, now let's talk about IP over DWDM. IP over DWDM. DWDM transceivers installed in your router or your switch. Basically, that's it. We've taken out this muxponder, this transponder, and you can put these guys right in there. That's where the 400 gig ZR plus stuff has gotten so popular, because now you have options. Now you still have to mux the signals. You still got multiple colors. You still got to amplify. You still got to do that other stuff, but you can eliminate your muxponder and your transponder. Yeah, these are a variety of the different terms that people use when they're talking about IP over DWDM. And I hear them constantly, all these different versions of it, right? So routed optical, converged optical, it's the same thing. So here's the basic idea. You've got your two routers, two different sites, and it's a long ways in between. So you need DWDM, or you've got a lot of bandwidth, you're fiber limited, so you want to put a bunch of stuff, a bunch of channels. So you buy muxponders, everything's great. Well, if I got rid of my muxponders and I could put the colored optics right in my router, I just eliminated a couple boxes, right? Nothing to manage. Works like a charm. I'm not really going to be able to get into some of the things that don't really work with this today. Again, come by and see me afterwards. But in terms of operationally, there can be some difficulties depending on your router vendor, the software they're running, et cetera, the ports that you can use that can handle the higher power levels of the DWDM transceivers, et cetera. But this is a pretty simple concept. The idea being you can save some money, and you can, but you got to be prepared for the other parts of what you need to do. For example, you need to add stuff to do it. You got to add filters, you got to add amplifiers. Maybe you need to consult on how some of this stuff works. So you're not done. So if you've just got one channel, great, but as soon as you get that second channel, you need some stuff. So this would be an example. You need a mux demux, whatever technology, thin film, AWG, or WSS. You probably want some optical channel monitoring. So you got all these different routers from different vendors even, and now what are the power levels for the different transceivers? Is it been tuned correctly? Is it red? I told it to be red. Is it red? You can check that with the channel monitor. But of most importance here is the power levels, Because once you hit that first amplifier and you start sending stuff out, now you got problems with power imbalance. And then we're going to talk about an OTDR here in a minute, but that's another key element that's very, very helpful in this scenario. So all well and good to put your colored optics in your router, but just keep in mind you need these other things as well. Right. Questions? Can I deploy an IP over DWDM solution without colored optics? It's not a trick question. Or maybe it is. Couple more people, wake up your phone. One more. I know you're out there. There you are. Yeah, no, you can't. I mean, that's the whole idea. It's IP over DWDM. So if you don't have a colored optic, what ain't IP over DWDM? Can I deploy IP over DWDM without a mux-demux filter? Don't be too quick in answering this. Okay. Yeah. I only got one channel. If I only got one channel, what do I need a filter for? I don't know why you're doing IP over DWDM if you only have one channel. Maybe get a long distance or something, but yeah, you can do it. Okay, let's talk about OTDRs. Good. Optical time domain reflectometer, right? So I think everybody's got one somewhere in the back room. You know, they're about yay big, or the smaller guys, new stuff. It characterizes the fiber by sending these pulses of light down the glass and looking for reflections coming back. It identifies faults, breaks, bends. Yes, it can identify bends, splices, problems, connector problems, all the stuff that's happening. And in doing all of this, it's going to be able to tell you the attenuation of the glass and the length of the glass. I love this. Yeah, there's a lot of squirrels. Urban areas, 2,150 squirrels per square mile. 10 squirrels per acre. That's a lot of squirrels. And this is exactly what they do. Those teeth are always growing. I think it's like 9 inches a year or something ridiculous. This is real. So, right, be aware, right? Or you got this guy. Same thing, digging up in the wrong place, or that glass wasn't supposed to be there, that kind of thing. So these fiber faults, you need to find them, and you need to find them quickly. So no more do you need to send your tech out, go to the end, disconnect the equipment, plug in your OTDR, let's see what's happening, where's the break? No, this stuff is integrated now. So you can have an integrated OTDR of modest capabilities. It's not going to be the all singing and all dancing device that you have on the bench. But the principle here is you're going to send these pulses down the glass, and you're looking for stuff coming back. And when you get these reflections, these events, they get reported and tabulated, and you can do stuff with that. So, for example, here, event 1 and event 2, maybe they're poor splices, or it's a patch panel with connectors that's got some kind of misalignment. I don't know, it's something, but the light's still passing through. Event 3, however, is the end, right? That's the end of the glass. That's where the cut is. That's where the break is. And so measure the time it takes for the signal to go there and back. You know the speed of light and glass. It can tell you the distance. Very handy. And so within a second, you can get a trap that'll tell you where the break is. I swear I'm not doing anything. Is it there? Okay. Maybe there's something under the floor here. I don't know. I'll stand back. Most common stuff is, you know, you didn't click the connectors all the way in. The MPOs, you know, all these multi-fibers, they all have to be aligned perfectly. And so you may get one that's pushed in or something, so you get this little air gap. And so the fiber section of this talk, which probably won't get to, talks about that. When you have two different types of materials, in this case, glass and air, you're going to get events. You're going to get light bouncing off of that. Clean your fibers. I think I've got 3 slides on cleaning fibers. So important. Patch panels. Did you clean the inside glass that's built into the patch panel? We see patch panels are the death of so many networks because it seems so simple. You're just going to plug a fiber in and everything's great. But the thing you're plugging it into was put in there like 5 years ago and nobody's used it, right? And it never tested, whatever. So these are the kind of things that the OTDR is going to identify for you. So this idea of refractive index is much more of this on the fiber section that we probably won't get to, but the idea here is that the OTDR is going to identify these events that are different materials, the glass, air, glass, dirt, misaligned glass, the APC, UPC, connectors and end faces, all this kind of stuff. That's what we're trying to see here. So the refractive index is what makes this possible. The differences in the materials. All right. Which of these is not the purpose of the OTDR? Locates bad splices, identifies fiber problems using light pulses, locates dirty connectors, improves back reflections. Okay. Right. Doesn't help with back reflections. It measures them. It sees them. Those are the events. Okay, now what you've all been waiting for. ROADMs and FOTMs. A reconfigurable optical add drop mux, that's your ROADM, and a FOTM would be a fixed. So the key elements we talked about earlier on the filter stuff, the ROADMs, that's the WSS, so that's your ability to redirect the light, to do things with the light by simply talking to the LCOS array. Whereas a FOTM is going to be built out of the thin film or AWG filters. And so that's fixed. But it has similar capabilities, and we'll talk about that in a second. So going back to this example here, just to refresh your memories, I know you all memorized this diagram already, and you know how this works, like it's something you taught in grade school, but the common port coming in, all that light gets separated by the grating and some focusing optics, shined on the LCOS array. You can apply voltages to the LCOS array and send the different colors out different ports. So that's your principle. And so in doing this, you're able to add channels, drop channels, block channels. We're going to talk about that. This is a really primitive view. This is not how a 2-degree ROADM is necessarily going to get built, but it's giving you the idea. It's a good comparison for me to show you the FOTM, the equivalent for the FOTM. So you have this WSS at each egress and ingress of the box, right? So the dotted guy, that's the ROADM. That's a 2-degree ROADM. And so you've got your stuff coming in from site 1, going through the WSS demux, and I can say, I want this color to go across the red port, out the switching port that's red, or I can send it out the black guy, and that's an add drop channel. And so I can change that in the WSS. And so that's the idea behind this. So I have the add drop stuff, and I have the express channels going through, and you can change it at any time. In a FOTM, since the mux and the demux are fixed, the colors are what they are. They can't be moved. And so if you wanted to express some channels through the FOTM, you have to externally apply some jumper cables. Pretty straightforward, but you gotta send somebody out there, or you gotta do it in advance and have sort of express channels pre-provisioned. But this is super simplified, but this would be a comparison of a 2-degree FOTM versus a 2-degree ROADM. And there's other capabilities we're going to talk about here in a second that the ROADM provides you that you can't get with the FOTM. CDCF. Show of hands, anybody know that? Any heard about CDCF? Oh, not too many. Okay. So colorless, directionless, contentionless, flex grid. Yeah, it's a mouthful. I'm going to tell you what all those things mean. But that's a key characteristic of a ROADM, what people look for in a ROADM. I want a colorless ROADM. I want a directionless. I want a flex grid, whatever. So it's helpful for you to understand what does that mean. A lot of times we talk to people that, yeah, I want that CDCF guy. Well, what do you want it for? What's your goal in designing your network, and what kind of things do you need that to do? And it turns out, well, maybe they don't need contentionless, or they don't need directionless. So it's important to know these things. Channel equalization and channel blocking. So these are all important qualities of a ROADM that you don't get with a FOTM. So I'm going to use an example here. So I got a 4-node ring, and all the sites have add drop, but I've just labeled site 2 here with some add drop. So a colorless ROADM is any color can be assigned to any port and be reconfigured. So in this example here, on the left, I've got circuit 1 is red. I've made it a frequency, we're using the color red. And for whatever reason, I don't want red going through site 3 to go to site 4 anymore. I want to change the frequency. I don't have to go out there. I don't have to send anybody out. I don't need to change any of the optics. I retune my optics, and I talk to the WSS, this colorless ROADM, and I can say, hey, this is now blue going through here. So that's what colorless means. Directionless, so that means I've got a circuit, same circuit 1, and it's going out around site 3, and maybe I've got a problem at site 3, I need some kind of protection, or for some reason I just don't want red going that way anymore, it's a more expensive route, I can redirect it out through site 1. So that's directionless. I didn't have to send anybody out to do this. So if the ROADM has directionless capabilities, there you go. And now contentionless. So the idea here is I've got 2 different circuits, and I want them both to be red. It seems like simple enough. I can send red out east and the other out west, but if you look at the WSS technology I showed you earlier with that LCOS array, red can only go out one port. I can't send the red to switching port 1 and switching port 2. It can only go out one place. So a contentionless ROADM, therefore, must have more than one WSS. It's got to be able to send red out 2 different directions. So that's the idea behind contentionless. And then, of course, flex grid, we looked at this already. So I can carve up my spectrum any way I want, and I can change it anytime I want. So if these 100 gig signals, for example, turn into 400 gig signals, well, I can just increase the amount of spectrum that's allocated for those signals. And I didn't paint myself in a corner by buying a fixed, WSS or a ROADM, an AWG or a thin film, right? So that's the idea behind flex grid. I can change the grid size at any time. And that's really important, especially when you get to 800 gig signals and above. So a 150 gig channel in thin film and in AWGs, that's about the limit. You can get 200 gig. We have 200 gig thin film, but it's not much after that. The technology struggles to try to make that size channel in a thin film or an AWG. And so if you're looking forward to 1.6T or something else, yeah, keep in mind, you're probably going to need a flex grid solution for that. Channel equalization. So why is that important? So I have all these different colors, and they're coming from maybe different routers. If I've got IP over DWDM, and I've got multiple vendors, and they have different transmit powers, and I amplify these things, and so these channels get out of balance. They get some powers higher on these channels and lower on these channels, and each time I go through an amplifier, that delta becomes larger and larger. And there's a lot of phenomena, nonlinear effects that happen in the glass where you transfer some of the energy from some of these channels over here at these frequencies to these channels over here. And so you get this power imbalance. Well, your receiver, when it gets to the end of the line, it's got a min and a max. Like, you can't be too hot or it's not going to be able to recover the signal. And if it's too low, you're not going to be able to recover the signal. So you got to be inside that sweet spot. So that's the idea behind equalization. So you want to attenuate the high power guys to match the lower power guys, or you can do whatever you want, but you can adjust it yourself. So this is just a simple example. I've got all the DWDM stuff coming in on the left, and they're at slightly different power levels. I want to make sure they're all the same after I go through my WSS. So the WSS or the ROADM will have this equalization capability. Similarly, on the mux side, so if I've got a bunch of different channels coming from, I got a bright 400 gig from this one vendor, and I got a non-bright, and I want to make everything about the same power level. I can do that on the way out. And then channel blocking. So the equalization feature, we're attenuating the signal. The blocking is just, you just attenuate the hell out of it, just block it. So that doesn't pass through. So that provides you with some features like protection or contentionless. I can route things different ways by blocking the light from going that way, but I can let it pass in another direction. So these are all the important features of your ROADM. Steve mentioned this. This was the talk I did at Nanog on ROADM and FOTM comparison. And so there's a lot of details there, and I touched on it a little bit here, like PDL, really important parameter, and the differences between the thin film and the AWG versus the WSS. Well, this kind of summarizes what those differences are. So for channel routing, it's manual, right? With the FOTM, I got to have a jumper cable to do express. That's it. And it's all soft configurable with the ROADM. But PDL is unpredictable at best. And then if you had cascaded ROADMs, you've magnified the problem. So cascading devices, that's something to be aware of. Path protection, if you're trying to do path protection with a FOTM, you've got to use some kind of protection scheme, optical protection, which is, again, a couple slides at the end of the deck here, which you can look at afterwards. Or I do it at layer 2 or 3, do my protection there. With your ROADM, you can do layer 1 protection. I can block channels, I can reroute colorless, right? Those features enable protection. That's how that works. For management, the FOTM doesn't really have any software requirements because there's nothing to do. You don't talk to it. It's fixed. But for the ROADM, the WSSs are controlled. It's typically some proprietary software, but there's open ROADM standards and other standards that help customers to use multiple vendors. And then failure, so if it doesn't take power, how does it fail? So the FOTM, it's got a fit number of 1. He broke the fiber, somebody did something to it, damaged it somehow, and then the ROADM is an active device, so it's going to have a higher fit. Power consumption, these are not all that different. You need EDFAs all over the place. There's a lot of insertion loss with these filters, whether it's the FOTM or the ROADM. Optical channel monitoring, so you can do that with a FOTM solution. So we have that solution. You can come by our table, you can see what that looks like. You don't need a full-fledged ROADM to be able to do this optical channel monitoring. But then for the ROADM, you've got the WSSs. So those are going to really bump up the cost. And then OpEx, a little bit more complicated for the ROADM. You got to manage all this stuff and all these channels and what's going where, right? So you need a you need some kind of SDN controller. You need the NMS from your vendor, et cetera. But then the CapEx is the big differentiator there. So just a sort of a functional view here. Bless you. The top design, that's your WSS, and the bottom one is your thin film AWG technology, the fixed stuff. Notice in the top guys, those are DWDM for all the ports. So I can send multiple colors of any frequency into the ports of your WSS. Whereas for the fixed stuff, the fixed mux demux, thin film, AWG, that's one color per port. So that's why it's drawn like that. You see the red, orange. So that's one of the main differences there. And if you wanted to see what these components look like, again, come by, you can see the DFS and the DMD. These are the XKL products. So the other thing, we talked about this, the filters, right? So the filters, the channel bandwidth that's required for the higher data rate stuff, as the data rate goes up, you need wider and wider channels. And with a WSS, you're future-proofing that because you're able to adjust the channel sizes. So I can support 100, 400, 800 today, and well, you know, maybe I'll get to 1.6, maybe I won't, but if you do, you don't need to change out this infrastructure. So that's one of the real benefits of going with a WSS, the ability to do that. That's not the only way to do it, but you can cascade filters, and again, come by the booth, I can talk to you about that. But this is one of the big draws for using the WSS to try to future-proof your network. Okay, let's see here. Go back to some questions. Okay, a photom has colorless add-drop capabilities. Yes or no? You all know the answer to this. I'll let you. 4 more. Okay, good. Yeah. No. Right? Fixed channels. Every channel is red, blue, green, doesn't ever change. So the photom is fixed optical add drop using thin film or AWGs. A colorless ROADM allows any wavelength or color to be assigned to any port. So that's a colorless ROADM. Questions kind of got easier, didn't they? All right. Right. Yes. The answer is yes. A directionless ROADM allows any wavelength port to be routed to any line port. So directionless. Okay. That's right. Okay. Okay, so this is a bonus question. I got about 16 minutes here. I might have time to talk about some fiber stuff, but I like this question anyway. So regardless if we've not talked about fiber, is it safe to look at the end of a fiber? When? When does that happen? I know you don't know what these hazard levels, 1M and 2M and that sort of thing, they're hazard levels, so just kind of use common sense there. So when is it safe to look at the end of the fiber? Who's not playing? Somebody raise your hand that wants to answer this question out loud. When is it safe? Never. Never. You don't know what's on the other end of that fiber. You have no idea. You can't see it. It's not visible. and it only takes a second for you to permanently damage your eye. All right. I think we've done it. And then the statistics, I'm looking. All right, I don't need how to get the stats. I'll show them to you after. I don't want to take up everybody's time here while I try to figure that out. The stats are there. Okay, let's go through some questions. I got about 14 minutes, and what we'll do is if we still have some time left and you want to, and you're up for the challenge, I can talk a little bit about fiber. But first of all, we'll go through some questions.
I had a question. Sorry. Yep. My name is Dan. I'm with Optic Networks. I had a question regarding, you were talking about the FOTM, the fixed grid, and if you were going to do a basically not add drop at a location, you could just run a jumper between the two directions. Is that a feasible solution? I've been told to not do that, that you would need a device in between them to basically boost the signal. I guess it kind of depends on the distance, but.
You're told not to do that because what?
Basically because it would affect the light, and we would end up with low light on one of the two ends.
Well, so each pass through these filters, so I come in from the left, I go through the demux, I go through the red jumper, and then I go out the mux. So that's double the insertion loss relative to what the add drop would see. So yeah, there's going to be some insertion loss, but keep in mind, you've got amplifiers surrounding this. So, for example, here, showing the picture with amps, right? So there is going to be a lower power, but it really depends on the network design and that power relative to your other channels. It's depends. It could be negligible, but if you had a lot of these sites, it's going to add up. Same problem though with, same problem there with the ROADM though. You've got insertion losses. You're going to have double the insertion loss going through the demux, across the red to the mux, and you're going to amplify this stuff. But with the ROADM, you're going to equalize. So that would be the difference. So if your network is modest in size, then there's no problem doing this with your FOTM. The complexity will increase as you have more and more sites, and therefore you might need to consider doing something that can either equalize the channels or use WSSs and equalize them with that. Because you can equalize channels with something besides a WSS, but it's another device.
Okay. Thank you.
Yeah. Sorry, Steve, did you want to say something? Yeah, so I don't know if everybody could hear him, but he's talking about single spans. Again, it's a network. It's how complex your network is will dictate whether you can take advantage of a FOTM or you need a ROADM or a combination. You know what's going to happen if you don't ask questions.
Hi, it's Steve Donovan with Temporal. I'm still confused why you would need a ROADM today, just as far as like unit economics go for lighting a path. Like, it seems like it would be better to just have multiple point-to-point FOTMs.
Well, so the virtues are the capabilities of that ROADM. If you don't need to go out and make changes, if you're not moving red, oh, I need to make that blue, I need to make adjustments, the FOTM is perfectly fine. Stable, simple, lower power, lower cost, lower OpEx. if you need to start doing things like, I got a new customer at the add drop site, and I need to now drop a color there that I wasn't dropping before, and you don't want to send somebody out to do some cabling, then the ROADM might be a better option, for example. So it's really that trade-off, and most of the times what we hear about is the less I have to send a tech out to touch something, the better. Yeah, but good question. Yeah, this is only showing 2 degree. Yeah. Yep. 3 degree and up. Yep. So you would talk to a vendor about it and tell them what you're trying to do and what's your operational requirements and what kind of add drop you might have in the future or whatever, and hopefully they'll guide you in the right direction to a solution that makes sense for your network. Okay. Okay, you asked for it. I've got 9 minutes. Let's talk fiber. So here's a fun glossary. Okay, fiber. Yay. Cool stuff, right? Okay, here's the construction of fiber. And this is important, which I'll talk about here in a minute with fiber aging. But basically, you got your core piece of glass down the middle, right? That's the your size of your hair, smaller than the size of your hair. That's where the action's happening. Around that core is cladding, which is another piece of glass with a slightly different index of refraction that keeps the light in the core. And then around that, you got your jacketing and your buffer tubes to protect the glass that's in the middle. And we're going to talk about what happens when these jackets and buffer tubes start having problems, start aging, start having micro cracks, start seeing effects of where that fiber is. Is it hanging on a pole? Is it buried in a conduit that's submerged in water? Okay, so the refractive index. It's a measure of how much light bends as it goes from one material to another material. So the equation for the refractive index is the speed of light through vacuum divided by the speed of light through that material. So in this case, we're talking about glass. So the speed of light through vacuum, the index of refraction is referred to as 1. That's your base. And so everything is going to be larger, right? So the refractive index of a material, glass, water, air, whatever, is going to be larger than 1. Well, not air, but. So for example, in space or in a vacuum, the speed of light, 3 times 10 to the 8, the index of refraction is 1. And just air, the atmosphere is about the same. There are impurities that have a small effect on it, but let's just consider that air is about the same as in a vacuum. But in the glass, in the fiber, it's about 2/3 of that. So the speed of light is different going through the glass. And this is where hollow core conversations come in, and I'll talk about that briefly. So the refractive index of the fiber, therefore, is 3 divided by 2, or 1.5. So when you look at like a spec for optical fiber, SMF28 or LEAF or whatever, there's going to be a refractive index number associated with that. So it's going to be about 1.5. So this is the optical illusion, right? So you've got air-water boundary reflecting the light. This is the idea behind the refraction. Oh, okay. Well, I'm going to talk about that in a minute. So these are some of the common connectors. We already talked about MPOs, the LC, really common, SC, and here is an end picture of what the core, that's core and cladding right there. You can see if you looked at it with the microscope. The mechanical makeup of the LC connector is shown here. You can see the spring mechanism. So I always tell customers when they're pushing these things into a transceiver or a port or whatever, feel that spring. You want that spring mechanism to push back on you. You know you got it clicked in right, because that's what's going to keep the two end faces really tight together. So these are some other different connector types. So most everyone probably deals with UPC. That's the most common. APC, angled, is the second most common. Why would you go to an angled connector? Why would get an 8-degree angle on the end face? It's because of the back reflections. So you can get pretty good improvement on back reflections when you have two end faces that are at an angle to the direction of the light as opposed to perpendicular. I have seen problems with APC connectors and maybe some not so reputable vendors making some of these, and the 8 degrees is not quite right. Things are not quite lined up. And I talked about like ramen and how that works, and that's a specific example where the ramen wouldn't even turn on because it couldn't get through this APC connector because it wasn't a well-manufactured cable. UPC stands for ultra physical contact, and PC physical contact, and then APC. So yeah, the only thing to be careful about here is don't plug an APC to a UPC. APCs are always green. You'll see, like on some of our gear, we have a bunch of MPOs. Those are all angled, so they're all green. So it's easy for you to tell by looking at the color coding. So this is typically what you see. Yellow is single mode fiber, and various colors represent the different generations and quality of multimode fiber. So OM1 being the oldest stuff, and OM5 and later. Yeah, I have a microscope I was going to bring, but then I realized I wasn't going to have time to do this. So there's some nice graphics here as to what happens when you don't clean your fiber, or you damage it, or what have you. Don't take the cap off, until you're ready to put it into something, because this is what happens. And once this stuff is a disease. Once you get it on one end, you transfer it to something else, and then something else, and something else. And before you know it, you've got everything all over the place. You've got to clean inside your transceivers, inside your patch panels, not just your jumper cables. We talked about this when we were looking at the OTDR stuff, but what actually happens, right? If you don't clean this sufficiently, you're going to get more back reflections. You're going to lose power. You might have problems with a ramen. The OTDR will detect this. Typically, it's dirt or it's an air gap that we see as the reasons why you get an event in the glass. These are your typical kind of cleaners, right? This cleat-top guy on the left, and the top right guy, the blue guy, that's one you can stick into your transceiver port, or you can stick it into your patch panel, right? So it can go inside. And then the bottom right, that's your MPO cleaner. So all the tools you need to keep a clean environment. Best practices. I probably harp on this too much, but I've just seen so many problems and so much time wasted for something as simple as good hygiene. So you got a connector in your hand, take the cap off, clean it, put it in. Don't take the cap off, put it down, go get the cleaner, come back, or clean it and then put it down and then come back. You got to follow a good sequence, and this will keep your fiber plant clean. Dropping caps and stuff on the floor, throw it away. Don't reuse it. It's not worth it. So these are just a few things to follow. So handling fiber, right? So we'll talk about some bend insensitive fiber here in a second. Right, coming back. So you need to follow these principles when you're routing fiber, right? So you're going to go up the rack and over onto the tray, right? And you go up the rack and over the tray, and woof, you got a nice tight bend right there. This matters. This stuff matters. You're going to get reflections off of that. You're going to get light bleeding into the outer coating, going outside of the core and cladding. So you have to observe these bend radiuses or use bend insensitive fiber. So this concept of total internal reflection is just that. If the angle is too steep then the light is going to escape. And if you had like a little fiber tester, which you use a lot in some facilities, which has visible light in it, plug it into a cable and then bend that cable. Bend it all the way, and you'll see the light come shooting out of that cable. Bend insensitive fiber. So what they did here, they just added a trench around that core. So it's not just core cladding, it's a little trench. That's to help keep the reflections in, keep the light inside the glass. So bend insensitive fiber is very common now. So any kind of patch cables or anything you buy are probably gonna be bend insensitive. I'm out of time. Hollow core. So hollow core is, a subject all to itself, but the idea is it's air or some gas that the light's going through. And as I mentioned, the speed of light through the glass is 2/3 the speed of light in a vacuum. Well, the speed of light here is the speed of light. It's 3 × 10⁸. So some real advantages when it comes to AI clusters, interconnecting them and being able to improve the performance of their communication. So that's where this hollow core fiber comes from. And so here's that example. So the speed of light through that is going to make some improvements for you. Fiber aging. I'm at 0. Am I still okay? Okay. So so that outer coating of materials is really important. If you've got glass hanging from poles or whatever it might be, that material is going to experience problems over time. I'm talking about long periods of time. When I first got into this space, I'm like, how the hell is a piece of glass going to age, right? What happens? Well, it's not the glass. It's the stuff around it. And it's going to press on different areas of it. It's going to put pressure on a section of fiber, which doesn't break it, but it's going to affect the transmission, a particularly coherent transmission going through that section of the glass. So you have these different environments, like a dry environment, a wet environment, all these things breaking down that outer coating. And some of those materials are really good, and they have a really good life cycle, lifespan, and others not so good. So that's what fiber aging is really about. It's not about the glass, it's about everything else. Yeah, thank you.